Okay, Assalamualaikum. Today we're going to continue the last chapter. Okay, interfacing and communication. Today we're going to discuss more on handshaking, buffering, program I/O, and also interrupt. So as introduction, peripheral devices demand attention of microprocessor at various and predictable times during normal program execution. So peripheral devices, we are referring to our input devices and also our output devices. There are several techniques are combined to resolve the problem of synchronizing and handling input and output between a variety of different input-output devices. So we have a lot of input and output devices. So there are a lot of ways to handle it because we can see here, because I/O devices cannot connect direct to the CPU. Okay, and why? Since the format required for different devices are different, and that means some device required single piece of data. Okay, single piece of data like keyboard. Okay, some required a block of data. Okay, some expect the data sequentially. So sequentially means this one is like when you try to watch video, you need to be in correct sequence. Okay, and then some expect data parallel, so they expect more data at the same time, and the data have to be transferred parallel. Okay, and incompatibilities in speed make synchronization different. So we have to know that our peripheral devices is sending or receiving data at a different rate. So the rate of keyboard is 1 bit at 1 block data at a time, one single piece of data at a time. But for monitor, it requires a sequential data. Okay, a mean to individually address different devices. Okay, so therefore, each devices is addressed differently. That means we have a lot of peripheral devices. Okay, so that let's say monitor we address as 0. Okay, and then at 1 we address our keyboard. Okay, and then and so on. Printer for number 2, let's say. Number 3, let's say your thumb drive. Number 4, let's say your camera, and so on. Okay, so a way for peripheral devices to initiate communication with the CPU. So it's like you have to imagine it like a house. Okay, your bus. Okay, your bus is the main road. It's leading to somewhere. That somewhere can be your CPU. So each devices is the house. So each house must have different address. So why? Because each house accommodate different people. Okay, different family. Some are family, some are single, some are family of 4, some are family of 5. Okay, and efficient means of transferring data directly between I/O and memory. Okay, so sometimes we don't need the CPU to communicate. We can opt it out, but we need to know the address. Buses that support high data transfer rate means for handling devices with different control requirement. Thus, our input and output the module is needed. So since our peripheral devices, our input or output devices cannot communicate directly with the CPU, we will need the I/O module as the middleman, or we call it as the driver. Okay. So why we need this one? It is necessary because different format required by different devices. Okay. So as we discussed previously, monitor, keyboard, and printer operate at different speed and different bit transfer rate. Incompatibilities in speed between the devices and the CPU make synchronization difficult. So, as you know, CPU work at a very fast rate, and most of the peripheral devices work at a much more slower rate. Okay. And some device, okay, give burst of data, while some device need a streaming of data. Device control requirements that would tie up too much CPU time. So if without the I/O module, okay, if CPU have to manage the I/O, the peripheral devices on its own, so we will consume a lot of CPU time. So it's a waste of the CPU power. So that is the I/O module in this picture. Okay. So as you can see, I/O module is always in the middle, as it is the what do you call that? The middleman. Okay. So any input from the output input devices will be transmitted to the I/O module. Then only from the I/O module will be sent to the CPU, and also vice versa. So any output from the CPU must be sent to the I/O module first, then only can be sent to the desired output devices. Okay, so this is a more complex picture. Okay, so but it is still telling about the same thing. So the difference here is it show a lot of uh, our input or output devices here, and some of it, and one of it is sharing the device, sharing the module. Okay, so sharing the module is like when we normally this happen when we use the USB. Okay, so but no matter it is, it still have to go through the I/O module. So the I/O module will be selected by the I/O data register, and the data will be sent to the data I/O register, and how the CPU will select which one, which I/O device it will cater. It will depend on the address, I/O address register. Okay, so usually the address will come from the CPU, because CPU will select which one they want to cater, and the data can be either from the I/O module itself, from the input devices, or the data can be sent to the output devices. So I/O module function. The I/O module function recognize messages from devices addressed to it and accept command from the CPU. Provide a buffer where the data from the memory can be handled until it can be transferred to the device. Okay, so I/O module function is also provide the buffer. Okay, so the idea of the buffer, you can try it when you open a word. Okay, it freshly open. Okay, and then suddenly you type gibberish, but so fast. You can see that once you type, there will be a lag, then suddenly all the word is burst there. So that's the use of the buffer. It will save temporarily whatever you type until your CPU you can cater the data, can grab the data from the I/O module. Okay. So provide the necessary register and control to perform a direct memory transfer. Okay. So sometimes when you're transferring something, you don't need the CPU, like transferring data from a thumb drive to a hard disk, okay, or vice versa. So all you need is a direct memory access module. Okay. So physically control the devices. Okay. So I/O module will control the device. Okay, copy data from a buffer to the device from the CPU to its buffer, and to communicate with the CPU. So there are a lot of I/O techniques. Okay, it's different. So some use buffering, some use handshaking, some use program I/O, which is CPU control input output, and then some use interrupt driven, okay, external input control, and some use direct memory access control. So this is commonly used as a method of transferring data to bypass the CPU, like transferring that just now we said, transferring data from a thumb drive to the hard disk. So buffering, okay. So buffering is a method where buffer is like a temporary memory, okay. Hold the data and release a part of it at a particular time. Okay. So buffering is also used in printer. Okay. So if you try to print something, you will see that there will be a delay. Once you press the print button, it will not print directly. It will pause for a while. What you call it, spooling. Okay, so some of it's called spooling. Okay, they gather all what they want to print. Okay, then only the printer will start printing. Okay, so when you use buffering, the idea of buffering also, you can see when you transfer data, from YouTube. Okay, you can see that whenever you watch YouTube, the red line will be at the back, and there's some already received data in the buffer, colored as gray. Okay, so a region of memory used to temporarily hold data while it's being moved from one place to another. Buffer can be implemented in either hardware or software, but majority of buffer are implemented in software. So they don't use specific memory. Usually the buffer is what you call it is stored inside the main memory itself. A brief back and forth series of handshake. Okay, the second method, okay, the second IO technique, okay, is called handshake. So a handshake is a brief back and forth series of requests and acknowledgement to request a connection. So if the negotiation is successful, a connection is open. This connection is logically a full duplex connection. Full duplex means there must be a receiver, okay, there must be a sender, and the sender can send message to the receiver can send back message to the sender. It's like what you call it, telephone. Okay, so half duplex is one way, what you call it, one way communication. Web browser application use this technique. Okay, so usually the handshake happen when you try to use the internet most of the time. Okay, because you have to maintain a constant connection with the server. So to maintain the connection with the server, we use the handshake. Okay, so so from here we can see that the client is, this is our computer. Okay, this is our computer. Okay, so this is the server. It can be, let's say we say this is our island server. Okay, so our island server. So when we try to connect to the server, so first we have to send a message. And we will ask, are you alive? Okay, see, are you? We will check whether the server is on, or off. Okay, is it up or down? Okay, so we will say, are you alive? Then the server will say, yes, I'm alive. Okay, so and then you can ask, let's say this one, you can ask, can I connect to you? Okay, can we connect? Okay, can I talk to you? Can I what you call it? Can I get some data from you? And then the server will say, of course you can. Okay, uh, okay, and then in the middle there, so you will ask, can you send me a file on chapter 5, chapter 5, the first topic of chapter 5, for CSC 159. And the server will say, yeah, of course you can, of course I can. So this is the data for you. So this is handshaking. So aside from that, handshaking also will continually happen. Okay, that means once you already they already transferred the data. Okay, as long as your web browser is on the island. Okay, so the handshaking of this part will keep continuing. Okay, so that means I will keep asking, are you alive? Okay, yes, I'm alive. Okay, then they say, and then it will say again, do you want anything else? And then your computer will say, not for the moment. Okay, just want to check whether you are alive or not. And then it will continue happen, and then it will start again. Are you still alive? Yes. Okay, so why we need this to happen? Because we need to maintain the session. Normally, why the handshake is important, because we want to maintain the session. Okay, so another kind of what we call that IO technique, okay, is called program IO. Okay, so in program IO, input or output data and register address register in the CPU. Okay, input output data. Okay, it is in the CPU. So one word transfer per IO instruction. So address information for each IO device include for multiple devices. Okay. So full instruction fetch and execute cycle slow. Okay. So primarily used for keyboard. Okay, program IO, and then the other one is communication with IO module, the transmission of command through a network IO module or modem. So, this one they give example of the keyboard. Okay, so let's say, okay, so keyboard. Okay, for this one, the address of the keyboard. Remember, if you want to what you call it, if you want to communicate with the I/O devices, okay, this one. If you want to communicate with the I/O devices, okay, this one. Okay, individually address different device. Okay, so each device have their own address. Okay, so for this example, the address for the keyboard is 24. Okay, so the CPU will start at the CPU execute input 24 instruction. So the address of 24 is copied into the IO address register. That only. Okay, so address 24 is recognized by the keyboard IO module. So when you say I want to access device number address 24, so it will be picked up by the keyboard IO module. Okay, so why you need to know the module, because to indicate whether it's going to read or is going to write. So obviously, when you go to the keyboard, you want to write something to the CPU. Okay, so read or write. So in this case, will be write. Control line indicate that the instruction is an input. Okay. So, okay, so from the keyboard, you press the D button. Okay, so this is your keyboard, you press the D. So a buffer in the IO module hold a keystroke. So when you press the D, the keystroke, in this case, ASCII character 68. Okay, so the letter will be D. So actually what will be stored here is 68. But if you refer to the ASCII table, 68 is referring to D. Okay, so the data is transferred to the IO data register. So from D on the keyboard, so on the keyboard you press the D. Okay, so it will be transferred into the buffer. Okay. So from the buffer, okay, so from the buffer inside the IO module, then only it will be transferred into IO data register. So from there, it is copied to the appropriate register inside the CPU itself. So inside the CPU, it will be copied 68 based on the ASCII table. Okay. So the next one, okay. So the next one in IO technique is interrupt driven input output. So this one we focus using interrupt. So what is interrupt? Okay. So first we discuss about interrupt driven. Okay. So peripheral device may demand the attention of the microprocessor during normal program execution. So that's mean there is another program running. Okay, and then your device need an interrupt. So this is normally happen when you connect your phone to your laptop. You will see a message at the bottom, okay, at the bottom of the screen, what you want to do with the device. Okay, so what is an interrupt? A call for the microprocessor to interact or service the interrupt unit. Okay, so the interrupt will cause the computer to suspend the program being executed and jump into a special interrupt processing program. So that's mean let's say you are running program A, okay, and then there's an interrupt. Okay, so what will happen is it will complete the program A first until it's complete the cycle, then it will straight away do program B. Okay, so when you run the program B, and it will run the program B until it's complete, then only it will go back to continue the work on program A. Okay, so interrupt is a signal that causes the CPU to alter its normal flow on instruction execution. The idea is to free CPU from waiting for event and provide control for the external input. So pooling process. Microprocessor would do routine checkup for the peripheral devices to see if it is needs service. Okay. So a better system is an interrupt process where it allows the processor to continue normal sequence execution until there is especially needed attention. So that means a good system, okay, will so CPU will normally, okay, routinely, okay, what you call it, will always check for peripheral devices whether they need to service they need to connect to the peripheral devices or not. Okay, but a good system, okay, it will allow the processor to continue normal sequence execution. That means to run the computer, run the program normally until there is an interrupt or a special uh, need to service the peripheral device. It would be desirable to interrupt the normal flow of program to react to or service a special event. Okay, so modern computer provide interrupt capability by providing one or more special control line known as interrupt line to processor. So that means you can imagine like there's a special button on the CPU. So CPU is running a program. Okay, so let's say you want to interrupt, you need to press the button. So but instead of button, it's called interrupt line. Okay, so program counter, okay, may contain as many as two. Program counter. PC may program contain as many as 32 interrupt line. Okay. So there are two type of interrupt. So there are two type of interrupt. One is called hardware interrupt. Okay, this interrupt is being sent by the peripheral devices to indicate certain condition such as keyboard entry, printing problem, and power failure, or software interrupt. Modern CPU has a set of instructions to simulate an interrupt. For example, hop and interrupt. Okay. So hop, you can see that. Let's say hop. Okay, how is like when you try to print something. Okay, when you try to print something, there will be a pop-up. Okay, so once there's a pop-up, you cannot continue writing on the word file. Okay, so that is a how. The message sent through the interrupt request, okay, IRQ interrupt request line, will cause an interrupt. Okay, the interrupt will cause the computer to suspend the program being executed and jump to special interrupt processing program. So, okay, interrupt handler program is the action taken by microprocessor when an interrupt occurs. So, interrupt handler program. This is also known as interrupt routine. Servicing the interrupt. There are four steps taken by microprocessor to handle an interrupt. The microprocessor finish the current instruction until the end of instruction cycle. Okay, so that means, okay, when we want to help, we cannot help when what you call it when you are fetching. Okay, you cannot stop the process when it's fetching, decoding, or executing. Okay, it must complete until the data is being stored again. Everything is being stored again. Then only the CPU will start the interrupt process. Okay, so when they start the interrupt process, the normal operation will be suspended. Okay, so the microprocessor jump to location in memory where the interrupt service routine has been stored and execute the routine. When the interrupt routine complete, it will return control to the interrupted program. That means it will continue the previous program normally. Okay. So how we service the interrupt? Okay. So let's say before interrupt arrive, program A is executing. Okay. So this is program A. Okay. Stack of program A. The program counter point to the current instruction. So let's say this is for, let's say we say this is A, line 3. Okay, so let's say A3. Okay, so it's currently pointing to the A3. Okay, so when the interrupt is received by the CPU, the current instruction is being completed. Okay, so that's mean, let's say when we receive the interrupt, is executing at the halfway of the program of the instruction mission cycle 3, the A3. Okay, so before it can execute the interrupt, it need to finish the instruction until it's told back again the last value. Okay, so all the register are saved in the stack area, or it is a special area known as a process control block. Okay, so once it's completed, okay, it will update the PC into A4. Okay, but okay, so the A4, and let's say when the program A final value is let's say just now the value is 6. Okay, so once it completed the calculation, the new value is 9. Okay, so the previous value was 6, let's say. Okay, the input value is 6, so it's sent inside the instruction is being manipulated, and let's say the original value was 4, and the original value was 6. Okay, so 6 is sent and manipulated. Okay, so it becomes 9, so 9 will be saved at the register A. So all this value, okay, will be saved into the stack array. Okay, so that means the current result of program A, and where the execution will continue later, will be stored in the stack array. Okay, so the PC is loaded, the program counter, okay, the program counter is loaded with the starting location of program B. Okay, so that means one is stored the what you call it, the PC now is free. Okay, so the program counter now is free. So A is stored at the stack area at the value of 9, see, and then the PC for A, program A, okay, which is A4. Okay, the next line we need to execute is A4, will be stored at the stack array, okay, or the process control block array. Okay, so the program, okay, it will start to execute B1. Okay, so here once it be transferred, so B1 can be stored inside the program counter. Okay, so PC is loaded with the starting location of the B, the interrupt handler program. This cause a jump to program B. So since we say for program counter say next execute B1 instead of A4. Okay, so A3 was previously, so it changed to A4. Okay, A4 here. So B1. So the next one will execute B1. So it will straight away execute this part. Okay. So this caused the program to jump to B, which become the executing program. So once program B is complete, okay, so that means let's say the final value here is was what we call it, B is executed until B3, let's say. Okay, so when it is completed, so when the interrupt routine is completed, register R restore. Restore means just now we have the value of A9 here, right? Okay, and our previous program counter for A is A4. Okay, so that's mean, okay, the value at the program counter will be A4. Okay, and then the value in the register will be back to 9. Okay, and the original program resume exactly where it left off. Okay, so there are two categories of interrupt. Okay, so the first one is maskable and the second one is non-maskable. So maskable interrupt is the interrupt that you can accept. Okay, interrupt that can be selectively disabled. That means you can let's say, how do we call it, this one, like downloading something. Okay, so this interrupt, let's say usually if you have Adobe, okay, when you start your computer it will say download or remind me later. Okay, so that kind is a maskable interrupt. Okay, so non-maskable interrupt is the interrupt that you can never stop or can never disable. You will automatically or have to accept the interrupt, like power failure, like blue screen. Okay, so multiple interrupt. There are many different type input and output devices and event indicator connected to the interrupt line. So remember, there are 32 devices just now. There are 32. Okay, program counter may contain as many as 32 interrupt requests. Okay, so multiple interrupt can occur from time to time. Okay, so two different processing method used to determine which device initiated the interrupt are vector interrupt or pooling interrupt. Okay, so vector interrupt, the address of the interrupt device is included as part of the interrupt. The vector interrupt is faster than pooling because but require additional hardware to be implemented. Okay, so this is the example of vector interrupt. Okay, so let's say we got a signal, okay, at our interrupt request line. Okay, okay, we got a signal. Please do interrupt. Please do what you call it, routine K atau or program K. Okay, so uh, our CPU, okay, we straight away after it done the previous is complete the cycle, the machine cycle of the what you call it, of the previous program, we will straight away execute the interrupt by queuing the address, the starting address of the interrupt key. Okay, so when the address is there, okay, so it can straight away jump to the address. Okay, so but it need a partial of your memory. Okay, it provides general pooling. That means you pool all the addresses together. Okay, so it provides general interrupt that is shared by all devices. There is a common branch address for all interrupt. The program that take care of interrupt begin at branch address and pool the interrupt service in sequence to identify the interrupting device. That means, okay, we don't specifically know where the address. Okay, so in this interrupt pooling routine, there might be address for A, B, C, D, E until Z. Okay, so when interrupt K occur, okay, so what we need to do is we need to go to the general interrupt pooling routine to check the address of K. Where is K? Where is K? Where is K? Okay, then we found K. Okay, so when we found K, then only, okay, we need to find the address of key. Okay, so you find the address of key and then you pull device to determine which device, okay, the key device, then only you can jump to the key. Okay, so you finish up the key routine, then only you can continue with the previous program. So handling multiple interrupt. Okay, so interrupt can be handled by assigning priorities to each interrupt. A higher priority interrupt will be allowed to interrupt a lower priority interrupt. Okay, that's mean if you have original program, okay, and then you have interrupt program A, okay, that's your original program, and then you have program B and program C. If program C have the higher priority than program B, so program C can interrupt program B, even though you execute program B first. Okay, you don't need to wait the program B to complete. So lower priority interrupt will have to wait until a higher interrupt is completed. Okay. Most computer systems allow the system manager to establish priority for various interrupts. Okay. So how do we know the interrupt? The three methods to establish priority. So the first way is the logical way. Time sensitive situation has a high priority. Hardware, physical location of the device, and software assigning a priority number to each devices. Okay, so that means we assign when we develop the program. Okay. Okay, so how do we service multiple interrupt? Okay, so this is an example of I think this one is with the priority. Yeah. So the original program is this one. Okay, so you are running this program. Okay, and then suddenly you receive the message of interrupt A. Please do interrupt A. Okay, so what you will do, you will suspend the original program and start to execute what you call it, interrupt A. Okay, but okay, interrupt B has the higher priority number. So while executing interrupt B, you receive a message to do interrupt B. While doing while servicing interrupt A, okay, you receive a signal to service interrupt B. So since B have the higher, what you call that, priority compared to A, you will need to suspend A. Okay, that means you execute halfway. You suspend A, and then you need to straight away do the interrupt B. Okay, so for this example, you can execute interrupt B until it is complete. Okay, so once you complete interrupt B, you can continue again with program A. Okay, with servicing the program A. But while you are doing A, you receive the message of interrupt C, which also have the higher priority compared to interrupt A. So for that, you need to again suspend service A, okay, program A, and start to execute program C until it is completed. So once program C is completed, then only you can continue to execute program A until it's completed. Then only you can go back to continue to the original program. Okay, so this is servicing interrupt with priority. Okay, so usage of interrupt. The way which an interrupt is used depends on the nature of the device. There are several ways in which interrupt are used: as an external event notifier, as a completion signal, as a means of allocating CPU time, or as an abnormal event indicator. So external event notifier, that's mean, let's say, how you call it? If you use, let's say you use download accelerator, okay? When your download is done, okay, it will start to pop up on your screen. So that's mean that one is showing a completion signal. This one is not good. External event notifier. How, how do you say? Ah, like the new browser. Okay, we have the to service the what you call that notification. Okay, if you observe your browser when you open certain website, there will always a pop up. Okay, to ask you either to allow or to disable notification. Okay, to stop to reject notification uh, request. Okay, so that is an external event notifier. So some of the program, when you have such what you call it, such notification requests, they will block your website, like advertisement. Advertisement is a good example. Some website they display advertisement. Okay, like when you're using browser and you are using ad block, okay, advertisement blocker application. So some website will say, please, they will send external event notifier. Okay, they will send message like, please disable your ad blocker first in order to continue. Okay, completion signal is like download accelerator, or also force advertisement. Okay, that means when you get some advertisement, okay, they are forced. Okay, they are forced on you. You have to wait until it finish. Let's say for 10 seconds, then only it will give you the completion signal. Okay. Some interrupt are meant of allocating CPU time. Okay. And most interrupt will give you an abnormal event indicator. So to indicate some external device required example. Okay, so this one external event notifier is based on the keyboard. Okay, so you are running a program. Okay, and then interrupt occur. Okay, so when interrupt occur, so it will suspend your program. Okay, so you have to let's say the interrupt will be the what you call it, notification interrupt. Okay, so you have to select either yes or no. Okay, so if you select yes, so take action required. So maybe it will start to sending you notification on the browser. You select no, it will resume as usual. Okay, so this is example of external event notifier. So function signal, Okay, so it's also saying that direct memory access. So we can see that this one in downloading. Okay, to control the flow of data to an output device, interrupt service to notify the computer completion of a particular course of action. An example is printing process and DMA process. Printing process is like when you're done printing. Okay, some printer will send you a message or popping up back the what you call it the printer helper module. Okay, or when you download something, it will say download completed. Okay, when you use download accelerator and such application. So this one give the example of a printer handler interrupt. So you are running a program, okay, while you are printing something. Okay, while you are printing something, you continue to browse something, let's say, on the internet. Okay, so then you receive a software interrupt to print handler. Okay, so what will happen is you cannot do anything else. Okay, you have to click either OK or continue or print other. Okay, that's the example of printer, what you call it, printer interrupt. Okay, so if you click yes, let's say, okay, so if you click yes, it will ask, do you want to print more, and then you say no, and then only it can continue with the original program. Okay, so or not, if in this case, okay, so you can resume your work, okay, as usual. Allocating CPU time is used as a method of allocating CPU time to different programs that are sharing the CPU. The computer system provides an internal clock that sends an interrupt periodically to the CPU. Once the CPU receives the interrupt, it will suspend the current program and go to the next program. Okay. So this means just like switching between a program. Okay. So the example given here is, okay, you are currently executing program 1, okay, and then you got the clock interrupt. Okay, that means clock interrupt say stop program 1, start doing program 2. Okay, so program 2, okay, so operating system dispatch the program, so you can select the next program. Okay, you can either what you call it, resume or suspend, okay, to execute another program. So once you're done with this one, you can straight away continue with the what you call it, program 1. Okay. Okay. So abnormal event indicator used to handle abnormal event. Affect the operation of the computer. The event are directly at the problem within the computer system itself. The example is execution of an illegal instruction such as division by zero, non-existing code, or hardware failure such as power failure. Internal interrupt are sometimes called trap or exception. Okay, so this one you can normally see when you do programming. Okay, or how can we see it? Power failure, abnormal indicator. Okay, this one you get a message like, how we say that? When you have abnormal, when you have to force close a program, like you're running a program, okay, you have to force close. Like we can go to Google Chrome too, for example, like you are opening too much tab, and okay, and then suddenly it will pop up the message of wait until the page is load, or just close the page. So that abnormal event indicator. Okay, so I think that is the first topic of chapter 5. Okay, what we call it, the part A of chapter 5. Okay, we discuss about interfacing and communication, handshaking, which normally happen in what you call that, in network. Okay, buffering, which all normally happen, for example, in YouTube when you try to print something or when you try to write something. Okay, and then program IO and also interrupt. Okay, so I think that's all for this part. See you on the last part later. Assalamualaikum.